Okay, this presentation is about random variables, and we'll talk about the terms population, samples, means, and standard deviations as we proceed. We start out, a population is a set that's being studied. Some examples of these: we might be studying students at PSU. We might be studying houses at PSU. We might be studying the voters in a particular district, or we might be studying the bottles of ketchup produced on a particular day. Each of these is an example of a population. A sample is a subset of a population. So, for example, if we select 30 students whose ID numbers have been selected at random, that's a sample from the population of PSU students. If we select 12 houses whose addresses have been selected, hopefully at random by a city inspector, that is a sample of houses. If we get 1,000 voters whose telephone numbers have been selected for a telephone poll, that is a sample. And if we pull 50 bottles of ketchup randomly from the production line, that is a sample as well. Okay, now, a random variable is the association of a number to a member of a population. And the idea, you've got your population, whatever population you're studying over here, and you pick out one of those, and you have some way of associating a number to it. So, for example, for a PSU student, there are just dozens of ways we can associate numbers with you. We can say, how many credit hours are you taking? How much tuition are you paying? What are the fees that you are paying? How many dollars in scholarships did you receive? And what is your student ID number? All of these are numbers that we can associate with you as being a student at Pittsburgh State University. Now, we take these random variables and we can do things to them, and we do things slightly differently depending upon whether you're a population or we're taking the numbers from a sample. Population, here, this is what I call the real deal. This is what we really want to know. And when we take a population, we'll figure out what's the mean of the population. The mean of the population. We denote it by the Greek letter mu. Okay, and people have trouble with this. They say, they look at this, it looks like a U to them. They'll think I'm saying you, like a female sheep, but it's a mu, like you have a cow that's trying to be fancy and it's moving, and it's mu. And for the mean, you take the values of your random variable, you add it up. Okay, at each of this x1 denotes a particular variable. We denote each one of our values with a subscripted variable. We add all of these values up, and then we divide this by the number of values. And so here, this capital N denotes the number of members in a population. You set this forevermore. A capital N is the number of members in your population. Okay. Now, a sample, okay, we don't denote it by mu anymore, by a Greek letter. We denote it by x, which is x is the name of our random variable. and we put a bar over the top of it. I got a kind of an unfortunate spacing of the bar. That should be closer to the top of the X, but you're smart, you figure it out. We have a sample size we decide on. This is a little n. Little n is always smaller than big N, right? Because we're taking a sample from the population. The sample size has to be smaller. We add up the number, we add together what we have, these numbers from our sample, and then divide that by the sample size we've chosen. Okay. So population, sample, not that much different, but we do want to make a distinction. Okay. Because we're about to do things we're about to get fancy here. Okay. We're talking about variance. And with variance, we calculate it differently for population and our standard deviation, and our sample. Population and sample are computed differently. What do? We first, in order to get this, we first have to have computed our mean. Okay, and we go through, we subtract the mu from each individual element of the mean. We then square that. Okay, then we add that up, and then we divide that again by the number of numbers. So you know, technically speaking, what we've done here, we've created a new random variable from our data, a squirrely one, and we are taking its average, and when we get the average of that squirrely random variable, that is our population variance. Okay. Now, this is denoted by this Greek letter sigma, which it looks like you know, an O wearing a baseball cap. Okay, and it's got it on the right way, you know, looking out over its eyes, and it's looking out, has that little 2 sitting on the bill of the cap, and it's looking at this scary formula out here. Okay. Now the sample variance, okay, we do the same sort of thing. We do this calculation of the X bar, our sample mean, and we take that from each individual item in our data set, and then we square that and we add it up, and here is where it gets squirrely again. Instead of dividing by a little n like we would want to, we divide it by a little n minus 1. Okay. The idea here is this sigma squared, that's the real deal. This s squared is an estimator for it. And back here, this mu is the real deal. This sample mean is the estimator for it. Okay, so the idea is that this, you know, capital N is a huge number. Okay, and so we'll never be able to know this. This sample N is a smaller number. It might be 30, it might be 1,000, whatever, but it's a smaller number, and this X bar should be fairly close in some sense to the mu. Okay. Now the same thing going over here, that this s squared is an estimator for this. In order to get the math to work out right, and I'm not going to go any deeper than that, in order we have to divide here by n minus 1. Okay. Now we'll actually, in this course, we only use variance as a means to getting to standard deviation. Okay. The standard deviation is what we'll use, and we're going to work this to death. I mean, you will get sick of it. We have, in different contexts, we have lots of different ways of calculating it. This is how you calculate it with raw data. And so the population, what do? Well, you take that variance that you calculated before, right here, and you take the square root of it. Okay, and then you do the same thing with the sample standard deviation. You take the variance and you take the square root of it. It's just in the calculation of the variance, it's different. Okay. Okay, we've got some, this is the sort of thing that you can look at it and you think, oh, averages are easy, the standard deviation I'll never do and I'll never get right. But quite frankly, it's not all that bad once you get started at it. I've got some homework problems for you, and these two examples are taken from them. The first, I do a calculation of with population data. I take my random variable x and I add up all of these values. I get 178. Okay, I take the 178, and then I've got 6 values here. Count them, 6. I divide the 178 by the 6, and I get 29.6666666 forever. Okay, and everybody's question is, where do I round it off? And the students that like to work hard just leave the numbers go forever, and the lazy ones, you'd round this to 30 if you could. The rule we have set, and the rule we will follow, is that you round your data to 1 decimal place beyond the original data. Round your mean to 1 decimal place beyond the original data. So this all goes to 0 decimal places. This will go to 1 decimal place then. Okay. Now, to get the variance and the standard deviation, you go through each data item. You make a new column over here, and you take your 22 minus the 29.7. Okay, take that difference. That's negative 7.7. You square it, and then you put that value down. You do the same thing for each of these, and at the end you add it up. Okay, again here with the sample variance you go 2 decimal places. With variance you go with 2 decimal places beyond the original data. You take that sum, you put it here, you divide it by 6 because this is population data. You still divide by your capital N. You divide it by 6, you get this, again you round it to 2 decimal places. You take the square root to get your population standard deviation, and when you do this you get 6.1. Okay, you round this off to 1 decimal place beyond your original data. Okay, there you go. So your standard deviation and your mean will both be 1 decimal place beyond the original data. Okay. We can do this with sample data. Okay, I picked out another example, and here I decided just to put it all in the same table from the get-go. This first column X adds up to 382. You take that, you divide it by the number of data items. Okay, you round it off to 1 decimal place beyond the original data. Okay, you take that and you do 52 minus 54 quantity squared. Okay, make sure you get them in the parentheses before you square them. Okay, and do that for each of these. Okay, this gives you a sum of 525.72. Note that this is 2 decimal places beyond the original data. You take that, you divide this by 6, right, because this is sample data. Okay, and so it'll be little n minus 1. Okay, and you have this, then you take the square root of that, and it's that right there. Okay? And so actually work through these yourself. You have it out there, what it ought to look like. Take your own paper, work it out. Take the homework. Okay. Take the homework that I have posted on the LMS, the Learning Management System. Take it and make your own tables. Work it out by hand. Yes, it is boring. Yes, it is tedious. Do it. Okay. And I've even got the answers there. Once you're done, you can check your answers and you can see if you did it right. Okay. And so thus endeth the lecture.